In this video, we continue our discussion of Sturm-Liouville problems with a second example. Notice that we have the same differential equation that we discussed in the last example, f double prime plus lambda f equals 0. We're on the interval from 0 to L. And we're told this time that f prime at 0 is equal to 0 and f prime at L is equal to 0. In the last example, we just had the function value at 0 was equal to 0 and the function value at L was equal to 0. So this time we want to, just like last time, find the eigenvalues and the eigenfunctions of the regular Sturm-Liouville problem. Remember, a Sturm-Liouville problem is just a second order differential equation of a certain form subject to some initial conditions, or excuse me, boundary conditions on the function and its derivative at the endpoints of the interval of interest. And we're not just looking for a solution to this problem. We're looking for non-zero solutions to this differential equation that correspond to different values of this parameter lambda. Lambda is called an eigenvalue, and it turns out we're going to end up with infinitely many of these eigenvalues. And each of those eigenvalues will correspond to an eigenfunction. It's just another name for a non-zero solution of this differential equation associated with that number there. So we want to find those eigenfunctions and eigenvalues that satisfy the differential equation subject to these boundary conditions, which is a specific example of a regular Sturm-Liouville problem. Okay, now in order to do that, we tend to look at cases. We tend to think of how the value of lambda changes the solution of this differential equation. So I would start with the case where lambda is negative. You could start with the other cases, it's fine. And then say, okay, well, if lambda is negative, what do the solutions to this boundary value problem look like? Well, in that case, our differential equation would look like this. Maybe we'll say that lambda is equal to negative lambda sub star, where lambda star is positive. Then our differential equation looks like this in terms of lambda star. If I replace lambda with negative lambda star, I get this. And that is a homogeneous, linear, ordinary differential equation with constant coefficients. When we solve a differential equation that looks like that, we typically let f equal e to the mx. Now, many people will skip this step. I'm not going to skip it, at least for the first and second examples. Many students need a reminder of where that characteristic equation comes from. You take the derivative twice, you substitute into the equation. If this is a solution to this differential equation, then this equation must also be satisfied. F double prime, which is m squared e to the mx, minus lambda sub star times f, which in our case is e to the mx, that would have to be 0 if this function is a solution of that differential equation. Now remember, from the ODE class, we're trying to find the values of m that cause this function to be a solution of this differential equation. So to do that, we differentiate, we substitute, and then we say, okay, what values of m would cause this expression on the left-hand side to equal 0? To find the values of m, typically we simplify by factoring out that exponential. And exponentials are never 0. So we get this. Now that means that m squared would have to equal this lambda star, and lambda star is positive. So we're going to have m1 and m2 are plus and minus square root of this lambda star. So these are two real distinct roots. Now we do get two linearly independent solutions that look like this. I'm just abbreviating solutions SLOLNS. F1 equals e to the m1 times x, and F2 equals e to the m2 times x. but those are not the solutions that we typically like to write our answer in terms of. If you have like e to the kx and e to the negative kx, we can take a combination of those and get hyperbolic sine and hyperbolic cosine functions because of the definitions of hyperbolic sine and hyperbolic cosine functions. So rather than using these two, we can use hyperbolic sine of the square root of our constant times x there, and hyperbolic cosine of the square root of that constant times x. And we can do that because hyperbolic sine and hyperbolic cosine are defined in this way. Hyperbolic sine is this, hyperbolic sine of x. Hyperbolic cosine of x looks very similar, but with a positive sign there. So notice that this is just a constant times e to some power minus 1/2. That's a different constant times e to the same power, but with an opposite sign. So this is just a combination. A hyperbolic sine function is a combination of functions that look like this. So if I take 1/2 of f1 plus f2, I get this new f1. And if I take 1/2 of f1 plus f2, I think I may have said that incorrectly. If for this first one, if I take 1/2 of f1 minus f2, I get this first function. For the second function, if I take 1/2 of the quantity f1 plus f2, I get this. So these are two linearly independent solutions of the differential equation. So are these. But we're going to tend to use these because it just makes the computation a little easier when we are solving for the constants in our general solution, the constants that would cause our solution to satisfy the boundary conditions. Okay, that's a lot just to say that f of x is equal to a constant times one linearly independent solution plus a constant times the second. We're going to use these. The hyperbolic sine and hyperbolic cosine. And then we're going to say, okay, that's a solution, or that's a general solution to the differential equation. And I'll put that in our notes. Put a big box around this and say, use these when m1 and m2 are equal to plus or minus some constant. And not specifically these, it's going to be plus or minus that real constant, or it'll be hyperbolic sine of that real constant times x and hyperbolic cosine of that real constant times x for the two linearly independent solutions. So it's not specifically these, but some variation depending on the actual exponents there. All right, so we've got our hyperbolic sine and cosine functions, and we want to find C1 and C2 that cause this function to satisfy our boundary conditions. Now, notice our boundary conditions involve derivatives. So in order to use those, we need to compute f prime. So f prime is C1 times the derivative of this hyperbolic sine function. Remember from previous courses, usually calculus 1 or calculus 2, the derivative of hyperbolic cosine or sine is hyperbolic cosine. And then I've got a constant times x inside. The derivative of a constant times x is that constant. Then over here, bring your constant C2 down. The derivative of hyperbolic cosine is hyperbolic sine. The derivative of a constant times x is that constant. Okay, so we're going to substitute into this. And whenever we substitute using our boundary conditions here. So our first boundary condition is that f of 0 is equal, or f prime of 0 is equal to 0. So that means f prime of 0 equals this constant times C1. And then we've got the hyperbolic cosine of 0 plus this other constant times C2 times the hyperbolic sine of 0. Hyperbolic cosine of 0 is 1. Hyperbolic sine of 0 is 0. So we end up with this positive constant times C1 after simplification. Now that is f prime of 0 in general. we need f prime of 0 to equal 0. So we set this expression equal to 0. And then we say, okay, well, if this times this equals 0, that means one of these is 0. Since this is not 0, that means C1 must be 0. Okay. Now our second boundary condition tells us this. A C1 is 0, so I will just leave that off. And we're setting this, that is the simplified version of this f prime evaluated at L. Now we require that to be 0. So I've got this times this times this equals 0. The only way a product is 0 is if one of the factors is 0. Now lambda star is positive, so this is positive. Now if C2 is 0, then C1 and C2 are 0, and that would mean f is 0, which would mean we don't have an eigenfunction here. So we would like to assume that C2 is not 0 if we can. Then we've got this hyperbolic sign of a positive constant times a positive constant, and that's actually not 0. So the only way this could possibly be 0 is if this is 0, this is 0, or this is 0. So let's write that down. So if this, we need this to be 0, that's not possible because that's positive. That's never true. And we've got C2 equals 0. And I mean, or the hyperbolic sign function is 0. But again, remember that hyperbolic sign function looks like this. The only time the hyperbolic sign function is 0 is when the function or the expression inside is 0. And this is positive. So this is not equal to 0. And since this expression inside is guaranteed to be positive, that means we're over here. That hyperbolic sign function turns out to be positive over there. So this is positive and it's not 0. This is positive, so it can't be 0. So that means the only possibility is that C2 is equal to 0. So C1 is equal to 0 and C2 is equal to 0, which means that f is the 0 function. But if f is the 0 function, then we're not dealing with an eigenfunction. So that means that lambda cannot be negative. So let me restate that. So f equals 0 is not an eigenfunction because eigenfunctions are by definition non-zero solutions to the differential equation. And if that's the case, that means there are no negative eigenvalues. Okay, so that was our first case. Now let's look at the second case. Let's say that lambda is equal to 0. Now our differential equation looked like this. If lambda is equal to 0, we get f double prime is equal to 0. And that means that f prime is the antiderivative of 0. And of course, the antiderivative of 0 is just a constant, because the derivative of a constant is 0. And the antiderivative of that constant would give us f, because if I'm trying to get f and I have f prime, I just take the antiderivative again. We take the antiderivative again, we end up here. So this would have to be our function f. If lambda equals 0, then f is a first degree polynomial in x. And I think we all know that's true. So that's a solution of the differential equation. Now we need a solution of the differential equation that satisfies the two boundary conditions, and the boundary conditions involve the derivative. So let's compute f prime of x. The derivative of a constant times x is just a constant, so the derivative of the constant is 0. This constant c2 is 0. So f prime is equal to c1, and we have that f prime of 0 equals 0. So that means f prime of 0, in our case, it's just c1. We have to set that equal to 0. That implies that c1 is equal to 0. Okay, and f prime of L equals 0 implies that f prime of L, which is just c1, because there is no x over here. This is just the function f prime equals c1. It's just a function that crosses the y-axis at y equals c1. So if you plug in x equals 0, you're going to get c1. If you plug in x equals L, you're going to get c1. So f prime of L is c1 in general, but again, we have to set that equal to 0. But we already knew that c1 was equal to 0 from that. So all we know at this point is that c1 has to be 0. So we actually do get a solution. When lambda is equal to 0, f is just equal to c1, which is 0 times x plus c2. Now we're going to choose c2 to be 1/2. Then we have f of x is equal to 1/2 when lambda is equal to 0. Now we will call this first function f sub 0, and we'll call this value of lambda equal to 0 lambda sub 0. And so that's what we have right here. This eigenvalue of 0 corresponds to this eigenfunction. Could actually be any constant. We're choosing that constant to be 1/2. Okay, so we looked at the case when lambda was negative. We looked at the case when lambda was 0. Now let's look at the case when lambda is positive. Okay, if we let f equal e to the mx, differentiate twice. If we substitute into the differential equation, we get that. And that's equivalent to that. And that's equivalent to that because that exponential is never 0. Now lambda is positive. So that means negative lambda is negative. And that means when we solve for m by taking this square root of both sides, don't forget the plus or minus on the right, we get complex conjugate roots. Now remember from your ODE class, if your m1 and m2 are equal to alpha plus or minus beta I, then your two linearly independent solutions are y1 equals e to the alpha x cosine of beta x, and y2 equals e to the alpha x sine of beta x. In our case, alpha doesn't exist, right? Alpha is 0. And beta, that's the number, the positive number multiplying I, that's the square root of lambda. So our two linearly independent solutions are f1 equals cosine of square root of lambda x, and f2 equals sine of square root of lambda x. That's what this says right here. And that means that f of x is a combination of these, c1 times the first function plus c2 times the second function. That is the general solution of this differential equation under the condition that our lambda is positive. Okay, now we want to find the values of C1 and C2 that cause this function, this family of solutions, or we want actually the values of C1 and C2 that cause this function to satisfy the boundary conditions. And the boundary conditions involve the derivative, so we'll compute the derivative. Derivative of cosine is negative sine. So we're going to have negative sine of square root of lambda times x times the derivative of the inside. The derivative of the inside is that square root of lambda. Over here, we'll add C2, and then we multiply it by the derivative of sine. The derivative of sine is cosine. Got a constant times x inside. The derivative of cosine of a constant times x is, or sine of a constant times x is cosine of that constant times x, and then we multiply by that constant by the chain rule. Okay, now let's go to our boundary conditions. F prime of 0 equals 0. That tells us that f prime of 0 is this. Substituting again into our f prime, we've got negative square root of lambda times C1 times sine of 0 plus positive square root of lambda times C2 times cosine of 0. Sine of 0 is 0 and cosine of 0 is 1. You remember that sine starts like this, starts at 0. Cosine starts at the top. When x is 0, the y value is 1 on the cosine graph. Okay, so f prime of 0 would just be this in general, but we want our function to satisfy f prime of 0 equals 0. So we have to set this equal to 0 and solve. Now, the only way that product is 0 is if this is 0 or this is 0, but lambda is positive. So that means the square root of lambda is positive. So that means that C2 must be 0. Okay. And then we've got our second boundary condition, that f prime of L is equal to 0. So we have negative square root of lambda times sine, or C1 times sine of square root of lambda times L. We're going to set that result equal to 0. Now if you're saying, what about the rest? Plus this, but remember C2 is already 0. So that guy is gone. So we just have that. Now if this times this equals 0. The only way that happens is if one of these factors is 0. But square root of lambda is positive because lambda is positive. And we prefer, if we can help it, for C1 to be non-zero because we're looking for eigen functions. We don't want C1 and C2 to be 0 because that would mean f is equal to 0, and that's not an eigenfunction. So we're hoping that this doesn't have to be 0, but it might have to be 0. We'll see. But then the last piece says this is 0, or this is 0, but sine is actually equal to 0 infinitely many times because sine looks like this. So we're going to have that last piece must be 0. And remember, sine looks like this. It just repeats indefinitely forever. And lambda times L, or the square root of lambda times L is positive because of the assumptions that we started with. We're on the interval from 0 to L. There's 0, there's L. So L is strictly positive. And lambda is positive for this case. So we want the sign of this expression to be 0, but this expression has to be positive. So that means that the square root of lambda times L has to be pi, 2 pi, 3 pi, 4 pi, any multiple of pi. So we'll say n pi, but only for the values of n that would cause this right-hand side to be positive. So we want this to be true for n equals 1, 2, 3, and so on. Now we'll solve for lambda. Square both sides. And so you have lambda sub n equals n squared pi squared over L squared for n equals 1, 2, 3, and so on. And we just write that sub n on there because we actually have infinitely many of these lambda values. Lambda sub 1 is pi squared over L squared. Lambda sub 2 is 4 times pi squared over L squared. Lambda sub 3 then is 3, that's 9 times pi squared over L squared, and so on. So these are the eigenvalues for this particular regular Sturm-Liouville problem. This is a given regular Sturm-Liouville problem. And then the corresponding eigenfunctions come from taking these lambdas that you just found and substituting them into the form of the solution to the differential equation. And the form of the solution that we were looking at, where is it? Is right here. Now, remember, we've just found that C2 is 0. So that means this piece is gone. So the functions are actually going to look like this. It's C1 times cosine of the square root of lambda times x. But lambda is pi squared or n squared pi squared over L squared. So you've got C1 times cosine of n pi x over L. And we don't need that constant. So we will choose C1 to be equal to 0. Now this is an infinite family. This is one function for every value of n. And for n starting at 1, n equals 1, 2, 3, and so on. So rather than calling this f of x solution, I'm going to call it f sub n of x. So I've got an eigenfunction for every value of n corresponding to a particular eigenvalue. And we substitute these eigenvalues into the differential equation over here. And we multiply by the eigenfunction, the corresponding eigenfunction, and we take the second derivative and we add, we always get 0. So the eigenfunctions and the corresponding eigenvalues satisfy this differential equation, and they satisfy both of these boundary conditions. Since we've chosen C1 to equal 0, we've got these eigenfunctions. Okay, so a summary of, the answer to this problem is we have lambda sub n is equal to n squared pi squared over L squared. Now, when n is equal to 0, we'd have lambda sub 0 equals 0. And remember, when we looked at case 2, where lambda was equal to 0, we did have lambda equal to 0 as an eigenvalue. And we said in that case, the eigenfunction should just be a constant, and we chose the constant to be 1/2. So this will work for n equals not just 1, 2, 3, and so on. It's going to be 0, 1, 2, 3, and so on. And then f sub 0 of x was 1/2 by choice for us. It could have been any constant. We just chose it to be equal to 1/2. And f sub n of x will be equal to cosine of n pi x over L. And that's for n equals 1, 2, 3, and so on. So those are the eigenvalues and the corresponding eigenfunctions for this particular regular Sturm-Liouville problem. Now that's it for this time. We will look at another example next time, and then we'll look at some properties of the solutions to Sturm-Liouville problems as well.